Hi. Today we're going to be talking about phase changes, okay? Now, phase changes pretty much is the concept of changing from one state of matter to another, all right? And they usually occur at particular temperatures. Now, boiling point is the temperature at which a substance boils under normal atmospheric conditions. Also, the temperature at which a substance condenses. Keep that in mind that at that temperature, it depends on which direction you're going. All right, if you're going from liquid to a gas, we call it boiling. If it's going from a gas back down to a liquid, we call it condensing. All right, now for water, the normal boiling point at 1 atmosphere of pressure, which is basically at sea level, is 100 degrees Celsius. Remember, we always use Celsius in chemistry. Now, the freezing point, well, that's the temperature in which a substance either freezes or melts. Okay, again, depends which direction you're going. But both of those, with water at least, occur normally at 0 degrees Celsius. All right. Now, some phase changes are exothermic and others are endothermic. All right, depending if you're putting heat into the system or if you're taking heat out. Now, an exothermic phase change is one that releases energy into the surroundings, thus warming them up. All right, so in order to do a exothermic process, you need to remove the heat from the system. All right. Now, a good example of this is freezing. When you take water, you put it into a freezer. In order to make ice, you are taking the heat out of the water. So that is an exothermic reaction, all right, or process. It's a physical reaction. All right, so freezing is a process in which a liquid converts into a solid. It takes place at the freezing point. Condensation, same thing. If you have steam or gaseous substance like water, condensation occurs when you take the heat out of it and it condenses down to a liquid. Now, technically, we cannot see gaseous water. All right, we call steam gaseous water, but technically, steam are little tiny water droplets that are visible, and it's more it's more of a liquid state than of a of a gaseous state. But when it condenses, that's when we can start seeing the droplets. Now, hot gaseous water becomes liquid water once it cools off a little bit and it loses that energy. That often happens, for example, if you have an ice cold drink and you see that it's along the outside of it, you get condensation. When I was a little kid, I used to think that that it was actually sweating, and my mom would get upset if it left a ring on our furniture and so forth. But that's condensation. Basically, water vapor in the air, not from the liquid, but in the air, touches the cold container, loses its energy to the container, and then condenses down to a liquid. Okay? So it's a process in which a vapor converted to a liquid. And it takes place when the gas particles lose too much energy to overcome atmospheric pressure and their attraction for each other. Now, there's one other one called deposition. Now, this occurs when a gas skips the liquid stage and goes directly to a solid. Now, this occurs, for example, with carbon dioxide. You take carbon dioxide and you cool it off, it will actually freeze into dry ice, okay? Also, this occurs with snow forming up in the upper atmosphere or when frost occurs when it gets really cold. All right, under normal atmospheric conditions, we tend to have liquid water, but not always. All right, not always. Now, endothermic phase changes are the opposite. They're going in the opposite direction. Now, this requires energy from the surroundings, thus cooling off the surroundings, okay? Now, energy is going into the system. So one good example is melting. You take a solid and it's converted into a liquid. This also takes place at the freezing point. Another example is sublimation. This is the opposite of deposition. Sublimation occurs when you have like dry ice and it goes directly into a gas. All right. And it occurs when atmospheric pressure is not high enough to squeeze a gas into a liquid at a particular temperature. All right. This occurs with dry ice because carbon dioxide's intermolecular forces are not strong enough to make it into a liquid under normal atmospheric pressure. But if we take dry ice, if we take carbon dioxide and we squeeze it into a high pressure condition, such as in a CO2 cartridge for paintball guns, then you can actually get liquid CO2. If you shake it, it sounds like liquid inside. All right, but normally, if you're going from a solid directly to a gas, we call that sublimation. So dry ice does it, all right, because they are non-polar molecules. And then there's also vaporization. Now, vaporization is the process by which a liquid is converted to a gas. Now, normally we think of boiling as one of the types. That's just one of them. And that occurs at a high temperature. When it occurs at, basically this occurs when a liquid's vapor pressure, we learned a little bit about that, when the vapor pressure equals the atmospheric pressure. All right. And usually that occurs when you have the temperature increasing up to the boiling point. Remember, temperature increases, vapor pressure increases, and this would cause it to equal the atmospheric pressure, and boom, it ends up boiling. But it could also occur at normal low temperatures if you take a liquid and reduce the atmospheric pressure. All right. On the website, whatever, there's going to be a video that shows water boiling. And remember, since boiling is an endothermic process, it cools it off at the same time. Kind of crazy, huh? And it will actually, if you take away the atmospheric pressure, it will boil, thus losing energy, lowering its temperature. It will boil until it freezes, which is kind of a weird concept, okay? So it usually occurs at a boiling point, but it also occurs throughout the liquid. Remember that you have the bubbles occurring not just at the top, but at the bottom and all over. It's a full rolling boil, all right? Now, the other type of vaporization is evaporation. Now, this is the process by which particles in a non-boiling liquid escape the surface and enter into the gaseous phase. Now, this occurs at any temperature. It does occur at higher temperatures faster, but it'll occur at any temperature. And this is a factor simply of the vapor pressure. Higher the vapor pressure, the faster the evaporation. And since it only occurs at the surface, it occurs at a faster rate when the surface area is greater. I mean, if you think about it, if you take a glass of water and you leave it out, it will eventually evaporate. But you take that same glass of water and you spill it on the ground, it'll evaporate much faster, okay? And remember, it's independent of atmospheric pressure. It only depends upon the vapor pressure of the substance, okay? Now, vapor pressures of different substances vary widely. And remember, vapor pressure is the measure of the pressure exerted by a gas above a liquid in a sealed container. But technically, that's the answer. But I want you to think of it as the pressure that the water molecules that are flowing about, it's the pressure, the force that they're exerting to try and escape up into the atmosphere and become a gas. And remember, the atmospheric pressure is countering that, keeping it squeezed together as a liquid. All right? And it's related to the intermolecular forces that we learned about. Remember the dipole-dipole attraction, London dispersion forces, hydrogen bonding. All right? The greater the attraction between the particles, the lower the vapor pressure. All right? So the particles need more energy in order to escape. All right? So if you look at this diagram here, this shows basically a barometer, okay, which is where the atmospheric pressure is pushing down on the surface of this is mercury, and it pushes it up this tube, okay? And then if you have a vacuum in it, normally the atmospheric pressure is 760 millimeters of mercury, or 1 atmosphere. But if you put some liquid water in there, the water vapor pressure here, or the vapor pressure, of water, pushes down on it to a certain extent, and it pushes it down a little bit more so that it has a pressure of 24 millimeters of mercury, causing it the height to go down. Now, if you put something with less attraction between the particles, like diethyl ether vapor, okay, which is a non-polar molecule, this has a much higher vapor pressure. These are non-polar, so they don't have any attraction for each other, so they push out with a much higher vapor pressure, thus increasing in the vapor pressure and pushing the column down even more. All right. Now, vapor pressure, remember, increases with temperature. A liquid will boil when the vapor pressure becomes greater than the atmospheric pressure. That's technically when it boils. All right. So if the atmospheric pressure is at 1 atmosphere, as soon as the vapor pressure equals 1 atmosphere, then it'll start to boil. Now, before it starts to boil, it will start getting little tiny bubbles, and they start to form. They go pushing out. Yes, I'm free. But the atmospheric pressure pushes down, going, no, you're not. And it collapses back down. That's when you're heating up water and you start seeing little tiny bubbles starting to form. It's not technically reaching a full boil yet. Now, once the temperature reaches about 100 degrees Celsius, then the internal pressure of the bubble equals 1 atmosphere. Then it has enough force that it can form a full bubble, reach the top, and escape into the atmosphere as a gas. Okay? So the particles become energetic enough to escape. Now, here's the cool part. As I talked about before, if you change the atmospheric pressure, then the temperature at which a substance will boil will change as well. So if you increase the atmospheric pressure, that means the water inside has to reach a higher vapor pressure to overcome it, and therefore it has to reach a higher temperature. Now, this explains why pressure cookers work. Sometimes they're called magic pots, but they will cook food faster. Water boils at a higher temperature in them, thus cooking the food at faster rates. All right. I remember when I first got married, we wanted to cook some artichoke, okay? And I and my wife had never cooked artichoke before. We saw our parents do it, and it didn't take very long. So we bought some artichokes and we put it in a rice steamer. We just thought we'd steam it. Well, it took over 3.5 hours to cook them enough that you can actually eat the artichoke. However, if you put it in a pressure cooker, which is what at least my mom used, then you can cook artichoke in like half an hour. So the reason why is it cooks it at a higher temperature. The water boils at a higher temperature and therefore cooks the food faster. Now, this also explains why boiling points change with elevation. At higher elevation, there's less atmospheric pressure, which means the water boils at a lower temperature. Okay? So if you're cooking water or boiling water at sea level, it'll boil at about 100 degrees Celsius. But if you're cooking it at, let's say, up in Boulder, Colorado, which is even higher than Denver, okay, it's approximately 5,430 feet above sea level. Then the pressure, instead of being a full atmosphere, is only about 0.8. And if you notice, the boiling point is at a lower temperature. Okay, the higher up in elevation you go, the lower the temperature is. I ran into this problem when I went hiking and I was hiking through the Sierras, which, like Mount Whitney and so forth. I wanted to boil water to cook some rice. I forget what it was, but to cook some food. And it took a lot longer to cook the food because it was boiling at a lower temperature. All right. Now, this chart right here basically shows the energy requirements for heating and cooling a substance. This happens to be liquid. Now, as we know, with the specific heat capacity, you put some heat into a liquid like water, it will increase in temperature. But notice what happens right here. Once the water starts boiling, all of the heat energy that goes into it isn't going to raise the temperature. It remains at a constant temperature. The heat energy going into it is the energy required to remove and separate it into a gas. So it still has the same amount of kinetic energy. All you're doing is you're separating and removing it. Okay? And the same thing goes in reverse. You take steam and you make it into water. It does it at a very constant temperature. It's just all the energy that is being released is from that energy being, all the particles being separated, shoomp, coming back together. That coming back together releases the energy. Same thing happens down here with ice and water. As ice is melting, all you're doing is, normally under ice as a solid, they're sitting there vibrating and they have the same kinetic energy as water at 0 degrees. It's just that the water can now move about relative to each other. All right. So the temperature remains constant during phase changes. Once at the appropriate temperature, additional heat must be added or removed to cause the phase change. Now, the exact amount of heat involved in phase changes can be calculated using very simple formulas. Now, before you learned Q equals mCp delta T. All right, the amount of heat is equal to the mass times the change in temperature times the specific heat capacity of the substance. Well, with these, it's very similar, but since there's no change in temperature, there's no delta T, there's no temperature involved at all. So these just involve the mass, right? The more mass, the more energy required, times two possible variables called the latent heat of vaporization or the latent heat of latent heat of, not formation. I'll get to it in a second. But anyways, the latent heat of vaporization. Now, this is simply it's like specific heat capacity. It is the amount of heat required to boil 1 gram of a substance at its boiling point. And the formula for it is simply Q equals M times that variable, okay? Now, for water, it depends if you're using calories or joules. If it's calories, then it's 540 calories per gram. Or if it's joules, then it's 2,260 joules per gram. And this is what you use for either boiling or condensing. The key thing is it occurs at 100 degrees Celsius. Now, that's at fusion. The latent heat of fusion, delta H FUS, okay? This is the amount of heat required to melt 1 gram of substance at its freezing point. It's also the amount of heat released when 1 gram of liquid freezes into 1 gram of solid. All right. And again, the formula is very similar. It's mass times the delta H, but this time it's FUS, which is a different number. It's a much smaller number because, as we saw in the previous chart, it takes less energy to go between a solid and a liquid than it does between going from a liquid to a gas. All right. And you use this for both freezing and melting at 0 degrees Celsius. Now, I do have for doing these types of problems, I have some sample problem videos that I want you guys to watch. But that's it for this lecture, talking about the concepts. So if you have any questions, please make sure you come to and ask them during tutorial. All right. Thank you very much.